Greetings, ACT Specialist Commander King here. We're taking a look at how to solve combustion reactions. So there are a few tricks and tips to solving combustion reactions, but we know we always start with some kind of hydrocarbon, usually. We've seen cases where we've seen other fuels like maybe nitrogen or hydrogen, and certainly more things than just hydrocarbons can combust. Now, the key thing you've got to remember with combustion reactions is you always need a source of oxygen. Oxygen is such a key source for flames to keep going. That's why we try to smother flames and deny that oxygen. So think about, okay, well, what makes flames go out? Oh, right, if I don't have oxygen. So if I could smother that out, the reaction will stop if we can remove that oxygen. So that's a good way to remember that. And then the products are actually two very simple and commonly found products that we think about: carbon dioxide, which we breathe out. After we breathe oxygen in, our lungs, breathe out carbon dioxide, and the other product that we often see is water. So think about the car exhaust combustion happening in the car. There's water vapor produced, and that comes out at the exhaust pipe of the car. So that's why on cold days you see that steam coming out. That's just water coming out for the most part. All right, so now we figured out, okay, we've got oxygen, carbon dioxide, and H2O. I want to figure out how to balance this reaction. So we've learned a few tips, and one tip that's very helpful is we go in the order of CH then O, and it kind of is easy to remember it because we can see, oh, CHO. And that's generally a pretty good order to balance in, because what we'll find is that the oxygen is the trickiest one to balance. So let's get started, and I'm going to start with my C's. I'm going to take my own tips here, and I'm trying to balance the carbon here, okay, the carbon here. So I see I've got two carbon atoms here from this C2H6, and over here I see I've got this carbon, but I've only got one carbon atom. So what I'm looking at here is two carbon and one carbon here. Well, how can I correct that? Well, I've only got one CO2 right now, but if I make that 2, then I've got two CO2, and that makes this 2, and now I've got two carbon, and that makes the carbons A-OK. All right, so now moving on, I'm going to take a look at my hydrogens next. So I'm looking at balancing hydrogen now. And all right, I've got 6 hydrogens here, fair enough. I've got 2 hydrogens here, it seems. So I've got more on my reactant side on the left side than my product side, the right side. And I'm thinking, okay, I've got 2 hydrogens. How can I get that 2 hydrogen to 6? Well, if I put a 3 here, that gives me 6 hydrogen. And now my hydrogens are even. So my hydrogen atoms are balanced now. I've got the same in the reactants and the products. And now for the trickiest one, the oxygen. So why oxygen is so tricky? Well, it doesn't look too hard on the reactant side. I've got 2 oxygens there. But look on the product side. It's easy to just think, hey, I've got 4 oxygen, and write that there, and put a 2 there. But wait a second, let's not forget about our water here. All right. Now you might be tempted to say, hey, 3 times 2, that's 6 oxygen. But careful, in each H2O molecule, I only have 1 oxygen. So in reality, 3 times 1, I've got 3 oxygens. And in total, that gives me 7 oxygen atoms. So now I'm looking at this. I see 2 oxygen atoms on my reactant side. I see 7 oxygen on my product side. I'm like, wait a minute, 2 times 3 is 6, 2 times 4 is 8. Nothing quite equals 7, but it is okay to use decimals here. And if I do 2 times 3.5, that gives me 7. Now you're like, wait a second, that doesn't make any sense. How could I possibly have half of an oxygen or half of an oxygen molecule like this, right? So, these are oxygen molecules. It's not like I could just have half of them. That would be an oxygen atom. And you're absolutely correct. In terms of ratios, this is perfectly fine. It tells me the ratio. But if you don't like that, if you'd rather, have a more whole number type answer because it makes more sense to you, we could just multiply everything by 2. And if I were to do that, then I get 2C2H6 plus 7O2. I'm just multiplying everything by 2, kind of distributing like in math. And that's going to produce 4CO2 and 2 times 3 is 6 H2O atoms, and this is perfectly acceptable as well. Now, one thing I'm missing here, as you see from the flame, the reason why we do combustion reactions in the first place is to produce an enormous amount of heat or energy of some form, and then use that energy to do other things, to run our cars, for example. And so the whole purpose of combustion reaction is not to really blow anything up, though it certainly could be used to do that. It's also to produce energy that we can now make use of in different things. All right. Well, hope this was helpful. King out.